Hi everyone, today we are going to go over radioactive decay. So, you should know what isotopes are. We reviewed these before. Don't worry about this key term, it's a little hard to see here, but that should say nuclide. Okay, so isotopes, different number of neutrons. Alright, so a couple key terms. I'm going to go through these quickly. A nucleon is a proton or neutron. Again, anything in the nucleus is considered a nucleon. We know that protons want to repel each other, right? So this is a look at the nucleus here. So what keeps the nucleus from staying together instead of flying apart? It's what we call the strong force. So it's got to be really strong in order to overcome that electrostatic repulsion with your two positives. Okay, so strong force holds the nucleus together. So what do you think of when you think of radioactive? This is what I think of. If you watch The Simpsons, this is Blinky, and then radioactive symbol here. A radioactive atom is simply one that is unstable. So what makes it unstable? If you have too many neutrons or too many protons or too much energy as well. Okay, so this is what we call the band of stability. It depends on the ratio of neutrons to protons. All right, how does a unstable atom become stable? Through radioactive decay. So through radioactive decay, our radioactive isotope will release particles or energy in order to become more stable, and this is going to be key. Generally form a new nucleus here. Alright, so we're going to look at a couple of different kinds of radiation and a couple of different kinds of decay. First is alpha decay. So uranium-238 alpha decays into thorium-234. Remember that this is the mass number. Okay, it's not the charge, that's the mass number. So what has changed? So let's look at this equation. We've got uranium-238 over here, and then it becomes thorium, and then we've got this alpha symbol over here. How has the atomic number and mass number increased or decreased? So, looking at this equation, we can see the number of protons or atomic number has decreased by 2. The atomic mass has decreased by 4. An alpha particle is released, which is this guy, and that has an atomic mass of 4 and 2. If we look at the periodic table, we can figure out what element is that. So, if you look at your periodic table, what do you think? What element is that going to be? Helium is correct. So basically we're releasing helium. Helium is the same as our alpha particle. You can use those interchangeably. Alright, let's try an example together. You're going to have to write these decay equations. So write the equation for the alpha decay of polonium-218. So first thing you would do is you'd write polonium-218. You would get this number, the bottom number, by looking at the periodic table. So if I find polonium over here, I would see that it's got 84 protons. Okay, so it's going to follow that same trend. So if you see alpha decay, the first thing I would write is my alpha particle. You can also write helium, it's the same thing. So 4 and 2. 4 and 2. Plus, so we got two products here. Plus we're going to get, remember the atomic number decreases by 2, and the top number decreases by 4. So you want to look up what element has 82 protons. We take a look here. 82 protons is going to be lead, Pb. Oops. Okay, and that's how you do these. You can always check your work by adding the totals here. Notice 4 plus 214 equals 218. 82 plus 2 equals 84. So anytime you have alpha decay, you'll always get an alpha particle, and then your new isotope is always going to have 2 less protons, and the mass number will decrease by 4. What about beta decay? So in beta decay, a neutron is converted into a proton and a beta particle is released. Okay. So here carbon-14 beta decays into, that's going to be nitrogen-14, and a beta particle is produced. So the other symbol for beta looks like this. Again, you can use these interchangeably. They mean the same thing. I think E is a little easier. The beta particle is a high energy electron. As carbon beta decays, the mass number remains unchanged, but the atomic number increases by 1. Okay, so we're getting an extra proton here. Let's try that example. Thorium-234 beta decays. Write the nuclear equation. So we always start with thorium on the left. We'll have an arrow. We have to find out how many protons are in thorium. So I'm going to use my periodic table here. Thorium is down here. It's got 90 protons. I'm going to put 90 here. Okay, since this is a beta decay, I'm going to put my beta particle, which is simply an electron with 0 minus 1. Okay. If this is a 0 on top, I know that this number is going to stay the same. And remember, the atomic number actually increases by 1. So it's going to be 91. The last step, you just got to figure out what element has 91 protons. We look on our periodic table and we see it's protactinium that has 91 protons. Okay, so again, for beta decay, you always have this beta particle, and the atomic number will always increase by 1. The mass number will always stay the same. Lastly, we have gamma decay. So if you look at this equation, this is our gamma particle, which resulted in this big guy, the Hulk. So in gamma decay, unstable releases energy in the form of gamma rays. Both the mass number and the atomic number stay the same. It's just getting rid of excess energy. Okay, write the nuclear equation for the gamma decay of barium-137. For the sake of time, I'm not going to do this one, but yeah, so don't worry about that one. Alright, last thing I want to cover is how strong are these different types of radiation. So alpha decay is very weak. It can be stopped by paper. So your skin will definitely stop any alpha radiation. Beta radiation, or beta rays, will be stopped by a sheet of aluminum foil. And then to stop gamma rays, these are the most harmful. You're going to need several centimeters of lead. Okay, moving on. This is for honors only. So here we have 2 more types of radioactive decay. For electron capture, the nucleus absorbs one of the atom's electrons, changing a proton into a neutron. So here, the electron is going to be on the left side. So just be careful with that. This is kind of like beta decay, except the atomic number actually decreases by 1. For positron emission, we get a positron, which is the opposite of an electron on the right side. And so eventually the released the positron combines with an electron to emit gamma rays. In both of these, the mass number remains the same, and the protons decrease by 1. In both of these, a proton becomes a neutron. Okay? So, don't have time for examples of this, but you'll see it on your worksheet.